The lines on this graph were explained at the end of part 1 of the Class A takeoff lesson. Nevertheless, the red line represents the accelerate stop distance required following engine failure, and the blue line represents the takeoff distance required following engine failure. The graph we have just described can help us to understand how V1 is chosen. Remember, V1 is the speed at which, if the engine failure were recognized, then there is sufficient distance remaining to abandon the takeoff, and there is sufficient distance to continue the takeoff. If V1 was selected at a low speed, then this would be the distance required to accelerate and come to a stop, whereas this would be the distance required to continue the takeoff. Therefore, for the V1 to suffice, this is the amount of field length required. If there was that amount of field available at the airfield, then theoretically a V1 could be selected at such a low speed. However, if a slightly faster V1 was selected, then this would be the accelerate stop distance required, and this would be the takeoff distance required. Therefore, it is this amount of field that is needed to have a V1 at this speed. Notice that now the total length of field required is less at this higher V1. In fact, another line can be drawn on the graph called field required. You can see, therefore, that a V1 at the intersection point of the graph is the best V1 to use, simply because a V1 at this speed requires the least amount of field, or the least amount of runway. This V1 is sometimes called the idealized V1. It is also the V1 which makes the takeoff distance required be the same length as the accelerate stop distance required. And therefore, this V1 speed is also called the balanced V1, since it balances the required distances for the aeroplane. What this graph is also useful for is to see the effect of using either a higher or lower V1. For example, if for whatever reason V1 was increased to this point, notice that the accelerate stop distance required increases, the takeoff distance required decreases, and the total field required increases. However, should V1 be reduced, the accelerate stop distance decreases, the takeoff distance increases, and the total field required increases. Trying to figure out these points without the use of the simple graph would not be easy. So use this graph to help you understand the effect of increasing or decreasing V1. Before we continue with other V speeds, it is important to detail what factors can influence V1. In essence, whatever factors change either the accelerate stop distance required or the takeoff distance required, in other words, whatever moves the two curves, will affect V1. However, there is a simpler way to go through the list of factors affecting V1. In every aeroplane flight manual, there will be a set of tables and/or graphs which will allow you to calculate what V1 should be with any given situation. On page 18 and 19 of section 4 in Cap 698 are such tables. Examine the second table from the top. This table lists the three V speeds, including V1, against the aeroplane mass. This table can show us what the effect of certain factors are. For example, let's look at what aeroplane mass does to V1. If the aeroplane mass was 50,000 kilograms, V1 would be 129 knots. But if the mass was increased to 65,000 kilograms, then V1 would increase to 151 knots. Therefore, increasing mass increases V1. The next factor to affect V1 is the aeroplane configuration. Page 18 lists the V speeds for 5 degrees flaps, and page 19 lists the v-speeds with 15 degrees of flap. Therefore, comparing the speeds from these two pages should tell us the effect of what the flaps do to v1. On page 18, which is 5 degrees flap, a 55,000 kilogram mass requires a v1 speed of 137 knots. But on page 19, which is 15 degrees flap, for the same mass of 55,000 kilograms, the v1 speed is now 130 knots. Therefore, we can see that increasing flap angle decreases v1. The next factor to affect v1 is density, but this is a little harder to observe than the previous two factors. On page 17 of section 4 is a small table, which has temperature on one axis and pressure altitude on the other. This is the density accountability table. Under low altitudes and low temperatures, you will notice band A. This is a high density band, whereas band F is situated at higher temperatures and higher altitudes, which equates to much lower densities. We can now use these bands to see the effect density has on v1. Returning to page 18, notice that bands A, B, C, D, E, and F are in the speed tables. Taking a mass of 50,000 kilograms in band A, which is high density, v1 is 129 knots. But in band B, C, D, and E, the value of v1 is increasing. Therefore, as density falls, shown by going through bands A to E, v1 increases. The last two factors that affect v1 are runway slope and wind. Notice that at the top of page 18 and 19 there is a table which is titled Slope and Wind v1 Adjustment. If there were a downslope of 2%, then with an aeroplane mass of 70,000 kilograms, v1 would have to be reduced by 3 knots, whereas if the runway had an upslope of 2%, with the same mass, v1 must be increased by 4 knots. Therefore, downslopes reduce v1 and upslopes increase v1. The right-hand side of the table is the correction for wind. So, for example, if there was a 15-knot tailwind, then with a mass of 70,000 kilograms, v1 would have to be reduced by 3 knots, whereas if there was a headwind of 40 knots for the same mass, v1 would have to increase by 1 knot. Therefore, tailwinds reduce v1 and headwinds increase v1. Having finished discussing the main factors affecting v1, there are other influences, however, which may or may not change the value of v1. Two influences on v1 in particular are the speed vmcg and vmbe. In Cap 698, on page 2 of section 4, we see the definition of v1. But more importantly, at the end of the paragraph, we read that v1 must not be less than vmcg, and not greater than VR, and not greater than vmbe. Since v1 must be between vmcg and VR and vmbe, then depending on the values of these speeds, they may or may not push v1 to be higher or lower than the ideal v1 speed. We will understand this better once we have discussed what vmcg and vmbe are.